Hello, yes, I'm back with some more questions on Newton's laws and things related to Newton's laws. So let's kick off with state the effect a net force has on the motion of an object. Right, there's a number of different ways you can say this. They all more or less say the same thing. I prefer to go back to our best form of Newton's second law, that force is the rate of change of momentum. I think that's the most insightful formulation of this that we've actually got, rather than just saying, oh yeah, net force changes the velocity of an object or it accelerates an object. I would say both of those descriptions would be sort of subsidiary to this one. I think sticking with this force is the rate of change of momentum is by far the most insightful. So I'm going to stay with that. Then for part B, we've got to start with define the impulse of a force. So impulse is the magnitude of the force multiplied by the time that it is applied to an object. So it's force multiplied by time. Actually, this is another reason why this is a good way to start with the net force and stating it in this full form of Newton's second law, because now we can see the relationship to impulse. We can see that force times applied time is the change in momentum. So we've got that built into it. We can also then see how this fits. If you think back to what we were doing in dynamics and kinematics, where we were talking about acceleration being the accumulation of acceleration being the change in velocity. So our acceleration multiplied by the time that the object is accelerating is equal to the change in velocity. And of course, that has come about because A is delta V over delta T. Well, we can see these things are the same. You know, if you multiply both sides by the mass, then we've got the force is the rate of change of momentum. We've then got our delta P, delta T coming out again. So it's the same thing here. So the accumulation of acceleration is the change in velocity. The accumulation of force is the change in momentum. So it fits with the language that we've been using. Now we've got a force F applied to an object. The graph below shows the force versus time graph. So we can think of this as being, just analysing it in the same way as we analyse the acceleration time graphs. So the accumulation of the force, as in the area under the line here, the force times the time, that is our delta P. That's our change in momentum, in the way that if this had been acceleration time, it would have been our change in velocity. So what are they saying here? The initial velocity of the object is 0, the mass is known. Explain how this graph can be used to determine the final velocity of the object. Right, okay, well, as I've just explained, the area is equal to the change in the momentum. So the area over the mass is going to be the change in momentum over the mass, which is the change in velocity, which in this case will be equal to the final velocity because the initial velocity is equal to 0. So it all flows through. All right, part C. Tennis ball is hit by a racket, as shown here. Right, so they've given us, let's see what's in the text that isn't in the picture they've given. They've given us the mass of the tennis ball there, 0.058. And they've given us the contact time. Just before contact, the racket head is moving. They've given us that. The ball is stationary, right? So the ball is starting at rest. Then after contact, they've given us the speeds in the picture. So that's okay, right? So calculate the mean force provided by the racket on the ball. Right, well, this is just using what we've explained at the top here. So our mean force, our F bar, multiplied by the contact time is going to be our change in momentum of the ball. So we've got the contact time 4.2 milliseconds. So all in all, we've got our mean force is the change in momentum is going from 0 to 52 times 0.058. And then we need to divide by our contact time, which is 4.2 times 10 to the minus 3. We type all of that into the calculator, we get 718, so 720 newtons to two significant figures. Right, estimate the mass of the racket. Right, it's interesting they put here estimate rather than calculate. So why might they have done that on there? Because it sort of throws you a little bit off your stride when you see a word that you maybe don't expect. Right, well, thinking this through and actually having an eye on the last part of the question as well is quite a nice way of putting it into your mind. Because it's saying here, why are you not going to get a calculated value which is going to be accurate if you're just working off of the numbers that they've given? This fits in with our idea of we've spoken a lot about closed systems. So is this a closed system? Well, they're saying here is during a serve, the racket head and the ball are in contact for this 4.2 milliseconds. Well, this isn't a closed system, actually, is it? Because you've got someone who's holding the racket. So there is another object, i.e. the tennis player, who is applying a force to the system. He's applying a lot of mass to the system as well. So this isn't a closed system that we've got going on here. So if we do conservation of momentum based on the data that they've given us, all of these numbers here, well, we're not taking into account the tennis player, so it is only going to be a rough estimate. But let's do our conservation of momentum anyway. We're starting off with 38 times the mass of the tennis racket. That's all we've got initially. And then we go to 32 times the mass plus our 52 multiplied by the mass of the tennis ball, 0.058. So our M is going to be equal to 52 times 0.058 divided by 6 when we rearrange all of that. Type all of that in, and we get the mass is pretty much 0.5 kilograms. So we've already covered now the last part, suggesting why this would actually be different, because we've got the tennis player there. I mean, this is something that we know from common sense. If you just throw the racket at the ball, it's going to behave very differently, not just because of, you're hurling it through the air, but the way it interacts with the ball is going to be very different. Because we don't have all this extra mass in the tennis player. Some of the momentum is going to be transferred to and from the tennis player. So you're going to have a momentum transfer. This is probably what you'd want to say in this last part of the question of what words are you going to use as a momentum transfer to from the player. So we haven't taken that into account. So it's not included in part 2. So yeah, that's a pretty involved question for first one up. That's a very nice one. Right, so next up we're stating in words Newton's second law of motion. Right, okay, so this is that the rate of change of momentum of an object is equal to the force applied to that object. So fairly straightforward on that. Then we've got figure 1.1. We've got the masses and velocities of two objects. Okay, they're moving directly towards each other. They hit each other and stick together, move with a common velocity v. Determine the velocity v. Right, so we want to do conservation of momentum on this one. Let's take positive going off to the right. So beforehand, we've got 15, well, 5 times 3 for A. We've got to take off 2 times 7 because it's moving to the left, and that is going to be equal to our total mass of 10 when they stick together, multiplied by the new velocity. So we've got 15 minus 14, so V is going to be equal to 0.1 meters per second, and that's going to the right. Determine the impulse of the force experienced by the object A. State its direction. Right, so the impulse is equal to the change in momentum. The change in momentum of object A is, well, final momentum is 0.1 times 3. Our initial momentum is that 15. So we've got a change of minus 14.7. on that. So that is, so they want the impulse and status direction. So we can say it's 14.7 Newton seconds, and that is to the left, because that's the direction that the force is hitting, is being slowed down, and yeah. So yeah, Newton seconds. Remember that for, well, you'd have to remember that for impulse. It's force times time is what our impulse is. Now remember that's come from our Newton's second law. So what we stated right at the beginning. So force multiplied by the time is going to give us that change in momentum. So force times time is Newton seconds. Explain, using Newton's third law of motion, the relationship between the impulse experienced by A and the impulse experienced by B during the impact. Okay, so Newton's third law is going to tell us that the force experienced by A is going to be equal and opposite to force experienced by B. And also we can say that the time of contact is the same. Contact is the same for A and B. So we've got the two things which are included here in our impulse calculation. We've got the impulse is force times time. So we've said that the time is the same for both, and the force is equal in magnitude but opposite direction. So the impulse, therefore, we got the impulse will be same magnitude but opposite direction, but in opposite direction. So yeah, it's quite an easy chain to go through on that one. But yeah, start with your impulse formula there, this force times time business, and that focuses you in on what to start talking about. You know, that's why they're bringing Newton's third law in, because it deals with these forces. It tells us that they're equal magnitude, opposite direction. So yeah, nice quick question. Okay, so now on to some car crashes. We've got start off, define linear momentum. Right, linear momentum is equal to mass times velocity. The linear momentum is a vector quantity. Explain why. I suppose there's a number of ways you can do this. I'm going to say, well, maybe there aren't that many ways, but velocity is a vector, so we can say that, and then we can say that a scalar multiplied by a vector, which is what we've got in our momentum calculation, is another vector. So that will do for those. The crumple zone of a car is a hollow structure at the front of a car designed to collapse during collision. Okay, right, so in a lab road test, this 650 kilogram car was driven into a wall, traveling at 7.5 meters per second and brought to rest in 0.28 seconds. Calculate the deceleration of the car. So acceleration is the change in velocity over the change in time. So that's 7.5 meters per second divided by 0.28. 7.5 divided by 0.28 is 26.8. 26.8. As usual, we're on two significant figures here, so we say 27 meters per second squared. What is the average force exerted by the wall on the car? Well, the average force is the mass times the acceleration, so let's multiply that by, what was the mass, 850, which gives us 22767. 22767, so that's going to be 2.3 times 10 to the 4 newtons, keeping everything again the two significant figures. Crumple zone of the car is designed to absorb 0.45 megajoules of energy before any distortion of the passenger cabin occurs. For this design of crumple zone, calculate the maximum speed of the car. Right, so this is all going to be the kinetic energy then. So we can have a half times 850 times v squared equal to, this is the most it can absorb, 0.45 times 10 to the 6. So we've got 9 times 10 to the 5 divided by 850 is equal to v squared. So let's start putting all of this in. 9 with 1, 2, 3, 4, 5 zeros divided by 850 and then square root it is giving us 32.54. V equals 32.54, which equals 33 meters per second, again to two significant figures. In a different test, another car of mass 850 kilograms traveling at a speed of 7.5 meters per second, makes a head-on collision with a stationary car of mass 1200 kilograms. Immediately after the impact, both cars move off together with a common speed v. Right, okay. So this is the usual conservation of momentum question. So beforehand, we have got 850 multiplied by 7.5. That's our initial momentum. The momentum afterwards is the total mass, 850 plus 1200, multiplied by v. So we just need to calculate that. 850 times 7.5. and then divide by, what's that, 2050, gives us 3.1 meters per second. So yeah, just a set of calculations really, that last one. Usual stuff that we're coming back to, a lot of momentum stuff going on here, which is just another reason to always think of Newton's second law being rate of change of momentum. Yeah, this is all about momentum, all of this. Newton's third law is conservation of momentum. Newton's second law is how momentum is changing. Newton's first law is that we're not getting changes in momentum until we're applying forces. It's only forces that are changing momentum. So all of this stuff is momentum based. Don't just think of it as being to do with forces and accelerations, because you're losing the depth there. You're losing the understanding that really this is all to do with momentum.